Perfect. Okay, so most of you handed in that guided practice from yesterday, but there was a couple of little glitches. And balancing equations comes down to little things. So if you look on, it was number 3. So you had iron plus copper 1 sulfate. So here's the deal. If you can't write, and I've emphasized this before, if you can't write the chemical formula for copper 1 sulfate correctly, everything else is just going to be a train wreck, okay? Because that's going to screw up the balanced equations. Then eventually you're not going to be able to do the stoichiometry because you don't have the coefficients right, okay? So you have to pay attention to the little things. Pay attention to the little things, everything else will take care of itself. So when you're going to write this as copper 1 sulfate, you have to remember, oh, here's CuSO4, and that's what some of you put down. It's like, oh, it's copper sulfate. Oh, it's cool, it is, but it's not. Because that copper has a charge of 1 plus, that sulfate has a charge of 2 minus, so you need to bring this 2 down here and go, oh, that's Cu2SO4, okay? So just because you see copper sulfate doesn't mean you can just write down the copper and the sulfate. You have to pay attention to those oxidation states. Now, one of the most important things you got to be able to do is recognize, hey, how is this reaction taking place? Is it a single displacement? Is it a double displacement? Is it decomposition? Is it a synthesis? So as soon as you see one element in an ionic compound, it has to be a single displacement reaction. That's it. So basically, these reactions happen because copper takes away electrons from the iron. The iron bonds with the sulfate, and the copper goes off by itself. Okay, so this is it's like you're dancing. Iron is more reactive. It kicks out the copper. It goes off by itself. So then out of this, and then you'd have to specify which iron that you get. Do you get iron 2? Do you get iron 3? Iron 2 is what you form most of the time because that's the most stable. So then you got to come over here and go, oh, that's FeSO4. And this is legitimately FeSO4 because the iron is 2 plus and the sulfate is 2 minus. Okay, so that's just going to be FeSO4. Then the copper is going to be off by itself. So this is the reaction that basically you all saw when you looked underneath the microscope when we did that very first lab. So on a single displacement reaction, you have a switch between something that's in a solution and something that's a solid. And those two switch places. Okay? So one goes into the solution and one forms out as a solid. So when you get this, then you can begin to balance it. Now, what I saw on some of your papers, some of you came over here and said, oh, I'll balance it by putting a subscript 2 out there, okay? You never, ever, 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 under any circumstances, balance an equation by changing the subscripts, okay? It doesn't work that way, okay? You balance it by changing the coefficients, but you never balance it with subscripts. So first off, you only have certain elements that are diatomic. Hydrogen, and then nitrogen, oxygen, fluorine, and then the halogens, okay? So copper isn't even one of the diatomics, okay? Copper is just copper, that's it. So you don't need that 2 out there. So then you begin to balance it with the coefficients. Then you go, oh, I got 2 coppers. Oh, I'll put 2 coppers here, okay? Now, I've got 1 sulfate, I got 1 sulfate, I got 2 coppers, I got 2 coppers, I got 1 iron, I got 1 iron, boom, it's balanced, okay? So it is, if you pay attention to the little things, the big things will take care of itself. But if you don't write those initial chemical formulas right based upon their oxidation states, you can't balance the equation, okay? So if you ever get into a situation where you're trying to balance an equation, and you can't get it to balance, odds are you don't have the right chemical formula, okay? You screwed up the oxidation state somehow, or something should be a diatomic and it's not. Anyway, so just general words of advice. Okay, any of the other, for those of you that still have those, or any of those you want me to go over? You're good. Going once, going twice. Sold. So if you have not handed in that white sheet of paper, I need it. So, let me, can you stop that camera for just a second? Okay, so we'll get to the lab in just a second. So on the packet, the chemical reactions packet, okay? So it acts, and this is going to be relevant to today as well. So one of the things we've got to revisit is the idea of mole conversions, okay? And that's going to play more and more and more of an important role. So like today, what you're going to do in the lab, you're going to take a piece of magnesium ribbon, and we're basically going to burn it, and it's going to combine with oxygen in the air. So one of the things that you'll see as we get into this is that when you look at these coefficients that are in front, they represent a ratio of two things. It says, oh, one iron atom reacts with one formula unit of copper sulfate, and we get one formula unit of copper sulfate out of it, and we get 2 atoms of copper. So it represents a ratio of atoms, but more importantly, it also represents a ratio of moles, and we'll go through why that works later on. So this also says, hey, 1 mole of iron reacts with 1 mole of copper sulfate, which yields 1 mole of copper sulfate and 2 moles of copper. So this is why at the beginning of this packet we kind of revisit this idea of moles, because those coefficients also represent ratio of moles. They don't represent a ratio of mass, okay? Listen to me, keep this in mind. This does not say, oh, 1 gram of iron reacts with 1 gram of copper sulfate to produce 1 gram of iron sulfate and 2 grams of copper. It's not what it is, okay? So those coefficients never represent a ratio of mass. They represent a ratio of atoms, they represent a ratio of moles, but it is not a ratio of mass. So moles is going to be like this common currency that we use when we talk about chemical reactions. So that's why it's so important that we get back into doing these mole conversions. So like on page 3 you got, hey, you got 0.2 moles of aluminum sulfate. How many grams is this? Show your work, okay? So here's the deal. Let's make sure everybody's cool with this. You got 0.2 moles of aluminum sulfate. What's the first thing that you've got to be able to do before you can do this entire problem? Let me give you a hint. It rhymes with formula of aluminum sulfate. Yeah, if you don't have the correct formula for aluminum sulfate, you're dead in the water. You cannot do this problem. Okay, you cannot do this problem if you don't have the correct formula for aluminum sulfate. So this is why it's so important that we figured out how to write chemical equations. So you have aluminum at 3 plus, you have sulfate at 2 minus. So take that 2, boom that, there you go. So this is 0.2 moles of Al2SO4 3. Because if you don't have that right, then your molar mass is going to be wrong and everything else is going to be wrong. So mole conversions, you're going to start with moles. You're going to put 1 mole down here. Where are you going to look to get the number that goes up there? Because you want to convert that into grams. So where are you going to look? Ramen. Periodic table. So you're going to add 2 aluminums. You're going to have 3 sulfurs. You're going to have 12 oxygens. Okay? Then that's going to be a really big number. This is one of the bigger molar masses that you're going to deal with just because you have such a large complex of that. Now, when you get down to the bottom one, it says 0.57 grams of copper. How many atoms is this? So when you get down to that one, you have 0.57 grams of copper, right? So remember on that moles, mole, okay, you've got mass, you got parts, and you got moles. So with this one, you're starting up here in grams. You've got to go to moles, and then from moles, you've got to go up to parts. So you have to do 2 conversions on this one. So And more, especially when we get into these big stoichiometric calculations, you have to put down the units. And I'm going to tell you this right now. As we go through this, if you're not willing to take the time to put down the units to show that conversion, I'm going to tell you straight up right now, I have better things to do with my life. If you just randomly write down numbers, and I don't know what they are, or worse yet, you don't even put down any numbers at all, you will get no partial credit. I am not going to waste my time trying to sort through what you did because you think you're too cool to write down units. So I'm going to tell you this right now. If that answer is wrong, you will get no partial credit whatsoever. I'm just going to stop, okay? I have better things to do with my life. I'm not saying that to be a jerk, but it's just the reality of it. You look at, when I work these, guess what? I go through and I put, grams of copper, I put grams of copper, I put moles of copper, I put moles of copper, I put atoms of copper. And I've been doing these for a long time. And the reason I still do that is because it eliminates mistakes, okay? And if there was a better, more efficient way to do this, I would show you that right from the get-go. So you're going to put grams of copper here. You're going to look at that periodic table. That's 63.5 grams of copper. That's 1 mole of copper. 1 mole of copper, or 1 mole of anything, contains 6.02 times 10 to the 23rd particles. So you're going to take 0.57, divide that by 63.5, multiply that by 6.02 times 10 to the 23rd. So that's the level of work that you need to be able to do. Okay, so hopefully, so we got the lab today. You need to continue to work on this packet. In an ideal world, if you can get through by tomorrow, the lab itself is pretty easy to do. It's not very complex. It's one of the more simpler labs we'll do. So by tomorrow, what I want you to be able to get through is through the bottom of page 6 on that packet. Okay? So the other ones, we'll talk about the different types of reactions. We'll deal with that more tomorrow. Okay? But especially when you get into these combustion of hydrocarbons. So if you can get through the bottom of page 6 for tomorrow and the lab, that's kind of where you need to be. All right, so let's chit chat about the lab. So what you're going to do is you're going to use a crucible. So a crucible is a ceramic cup, okay, that and it's designed to hold and withstand very high temperatures. So what you're going to do is that you're going to take a piece of magnesium ribbon, about like yay, okay, and you're going to wad that up into a ball that will fit down within that crucible. So if you look at that data table, borrow this for a second, okay, so on the data table, you're going to need a whole bunch of information. So you're going to need the mass of the empty crucible and cover them. So before you even put this magnesium ribbon in there, you're going to take it, you're going to put it on the scale, you're going to find that empty mass. Then you're going to put the magnesium ribbon in it. Then you're going to find that mass again. And then from that, you're going to find the mass of the magnesium. Now, notice it says in the instructions, show any calculations that are needed in the space to the right. Okay? So to get that mass of the magnesium that's reacted before heating, you need to do a simple subtraction. Oh, here's the mass of the empty crucible. Here's the mass with the magnesium ribbon. Oh, subtract that out. Boom, there's the mass, mass of the magnesium. Now, what's going to happen is that we're going to take this and we're going to heat it up. And it's a kind of a complex process because it burns rapidly, but we actually have to keep heating it and heating it and heating it to make sure that everything is fully reacted. So after you get this in there, call me over. I'm going to bring the really cool torch, okay? And I'm going to use this to light your magnesium. Theoretically, if you just heat it just in the Bunsen burner itself, it will light, but about half the time it won't light. So what I'm going to do is I'm just going to increase the odds by taking this kind of look like a little lightsaber, flame lightsaber, okay? And I'm going to use this to ignite the magnesium in there. So then what you want to do is there's going to be a lid that's going to go over the top of this, okay? right? These are fragile. Be careful. You're going to use those tongs, okay, to adjust that lid, okay? Be careful with this, because if you break the lid, then your whole mass system is screwed up and bad things can happen. So as you go through this, basically you're going to heat this up, and you're going to adjust the lid because you obviously because the oxygen is coming from the air. So we can't seal it up, because if we seal it up, then the oxygen molecules can't get in there and the oxygen can't react with the magnesium. So we need to have it covered, but we also need to have it like a little bit off center so that that oxygen can continue to flow in. So what's going to happen is that you're going to heat this stuff up again and again and again. And you're going to heat it like 3 to 5 minutes. Then you're going to let it cool. Then you're going to take a glass stirring rod, and then you're going to crush that up, and then you're going to add water to it. Okay, so the water can also provide a source of oxygen. And then, but the primary source is going to come from oxygen that's in the air. And you're going to crush that up. It's going to kind of make like a gray paste. And then you're going to heat it up again. Try to avoid getting that, after you crush it up a second time, try to avoid getting that magnesium paste on your stirring rod, okay? Or if you do, try and like scrape it off on the edges of that crucible, so that way it's staying within the system, because your results are going to be screwed up if you have, it's like cookie batter, and you carry a lot of that magnesium out with you on the end of that stirring rod. Well, that just kind of screwed up everything, because now you've got part of your magnesium oxide on the end of your stirring rod instead of inside the crucible. So, like I said, the lab itself is fairly simple, okay? You're just going to heat this stuff and heat this stuff and heat this stuff, let it cool, crush it, heat it again, heat it again, heat it again, and then find the mass of it. So what you need, so what you're ultimately after is that you're going to have the mass of the magnesium. It's going to react with oxygen in the air. So what you should see, hopefully, is your mass increases. So by however much the mass increases, that's how much oxygen that you added. So you're going to start with elemental magnesium. It's going to react with oxygen in the air. You're going to form magnesium oxide, okay? So what you're ultimately trying to find are two different masses. The mass of the magnesium oxide, and then from that, then you're going to figure out how much oxygen was added, okay? So two of these you will measure directly. The third one, you're going to have to do a little bit of thinking, like, how do we get that mass of oxygen? So again, I cannot emphasize this enough. When you're over here and you're doing any calculations, show me that subtraction. What did you subtract to get that number? Then, when you're going to come down here, you're going to write the word equation and the balanced chemical equation for the reaction between magnesium and oxygen. Then, what you're going to try and do is that you're going to try and calculate what we call these percent compositions. And you've done percent compositions. We did that when we did the hydrate lab. And we took the mass and the partial mass and we divided it by the entire mass. So what you're going to have is the total mass of the magnesium oxide. So when that says total mass, that's the mass of the magnesium oxide. Then to get the percentage of magnesium, you're going to take the mass of the magnesium, divide that by the total mass, and then to get the percentage of oxygen, you're going to take the mass of the oxygen and divide that by the total mass. Okay, so these two percentages of your magnesium and your oxygen should hopefully add up to about 100%, because you only have two things. You have magnesium and you have oxygen. So if I were to add the percentage of men and the percentage of women in this classroom, guess what? Those percentages should add up to 100. Okay, there you go. So that's how you can kind of check that you got this right. Now, you've got a whole bunch of conversions to do. Moles of magnesium were present before burning. How many moles of magnesium, of oxygen reacted with the magnesium? Then you're going to formula for magnesium oxide, then you're going to calculate a theoretical percentage of magnesium. Okay? Got it. Good? Okay, so let's go do science. Yes, you're going to be heating up some nasty stuff. Make sure that you're wearing your glasses. All right, stop that.